Morning, everyone. We're going to be continuing this week looking at machine learning and classifiers. Let me give you a few announcements for today. First of all, next week, we will have lecture on Monday, but office hours and labs and tutoring sections are canceled next week for Thanksgiving. Second, big announcement here, our final exam. We are going to be holding the final exam in person on paper. We've heard feedback about how the proctoring protocol was challenging, and campus has very kindly given us space. So we are going to have the final exam in person at a variety of locations. You'll be taking it on paper. If this is a problem for you, we'll make arrangements for you. We will be putting up a form where we're asking everyone to submit the form to indicate if they have any problems with this. And if this doesn't work for you, like for instance, if you're not here in Berkeley, no problem, we'll work with you. We will find alternate accommodations so you can take it online if needed. But the expectation is that the default will be a final exam in person. Same time, no change to the time, just a change to the location. You won't need a laptop for the final exam. Other standard announcements. Oh, I should mention on the final exam, we expect to have an ed post sometime today. So please keep an eye on ed, and there will be a Google form that we're asking everyone to submit to indicate, let us help find if there's people for whom this is going to be a problem. General reminder, homework 11, don't forget, due tomorrow. Today, if you want 5 bonus points. Project 3, the checkpoint is due Friday, and the final project is due a week from Friday. The complete project is due a week from Friday. This week in lab, we'll have a worksheet, and we'll have a chance for you to work on project 3 with your partner if you have one. Okay. Yeah, this is going to be new for a lot of you, taking an exam in person. Wow, it's new for a lot of course staff too. We'll have instructions for you on the ed post. Did I get the project deadline date wrong? Do the week after Thanksgiving. Yes. Not a week from Friday. The final project is due 2 weeks from Friday, not over Thanksgiving. I'm so sorry. Okay, here's what we're doing in class this week. We're teaching you a little bit about machine learning. So on Monday, Professor Adhikari introduced you to the notion of classification and some of the core ideas behind it. And today and Friday, we're going to dive into some code. We're actually going to go do it. We're going to go build a classifier. And in project 3, you're going to get a chance to work with machine learning and do a classification task. It should be fun. So these lectures here will also serve as prep for you for project 3, so that we do a detailed walkthrough of the classification technique you'll be using in project 3 and how to turn that into code. Before I dive into that, I see some questions in the chat. If you aren't on campus, no problem. No problem. Please submit the Google form. We will arrange for you to take the exam online. It will be at the same time. It's not a problem. We'll work with you. Okay, so classification. So Professor Adhikari showed you the main concepts of classification. I personally think of machine learning as one of the great breakthroughs of computer science of the past 20 years. It's enabled some really cool technology. It enables like Siri and voice transcription, and it's one of the core technologies that will power self-driving cars, machine translation from one language to another, many really cool things. It also, I think, has the potential to have some impact on society you will live in your lifetime. I expect you will see changes as a result of machine learning. And beyond the upsides, there's also potential downsides or risks with machine learning. For instance, already companies are starting to use machine learning and classification as their first filter for job applicants. They look through the resume and make an automated prediction about whether it's worth doing an interview for you. I've seen a proposal from our government of doing a first pass screening on people who are seeking a visa using machine learning to check for people who might be a particular risk. Criminal sentencing in a number of trials uses machine learning algorithms to predict whether the individual is likely to reoffend, and to help the judge make a decision about how long a sentence and whether to grant parole. And I've read news reports about one country that's using facial recognition, so another form of machine learning, to track individuals in a particular minority group there, and keep tabs on them for surveillance. So there are some potential risks of machine learning, and I think as a good citizen of society, it's important for you to have some sense of what this thing is and isn't. And so in this class, we want to show you one machine learning algorithm so you get a sense of this. Machine learning, there's lots more here that we could possibly teach you in this class. There are many more classes you could take to go deeper, but we're going to teach you one particular method called nearest neighbor classification. And I think maybe by the end of this, you will get a sense of a couple of different aspects of machine learning. One is, it's amazing. It's so wow that it's a really simple idea that turns out to be incredibly powerful in what you can accomplish. Second, it's so stupid. People sometimes talk about our artificial intelligence as computers becoming intelligent, and you will see from the technique we're showing you that it's just looking for patterns and it's doing something really dumb. And third, maybe you will see why the big fuss over big data, because as you'll see here, machine learning and classification algorithms rely heavily on having a lot of training data. They need a lot of data to work well to make good predictions, which then drives a lot of companies to want to acquire a lot of data, which then has a whole bunch of impacts on the technology world. So today and Friday, I will be showing you nearest neighbor classification. Then on December 1st, we will have a guest lecturer from Professor Ziad Obermeyer, who studies bias in machine learning. And I highly recommend coming to that talk. All right, so let me dive into it, but I'm just checking the chat here for questions. Yes, facial recognition uses machine learning. It uses classification. Many of the same techniques. I'm not going to show you how to do facial recognition in this class, but you could take more classes and you'd learn how. All right. So nearest neighbor classifiers. At a high level, here's how they work. We're trying to make predictions. We're trying to predict the label or the class or the category of some instance. So for instance, if I have an email that arrived in my inbox, a classifier might try to predict whether that is spam or not. If Amazon receives an order, a credit card order, they might try to predict whether that credit card is fraudulent or not. If a patient shows up at a doctor's office, the doctor might try to predict whether they have chronic kidney disease or not. So that's the label, disease or not, spam or not. And to make that prediction, we're using some attributes. For instance, to predict whether the patient has chronic kidney disease, maybe we're using lab test results from a number of different lab tests. So those are the attributes. And the nearest neighbor classifier is going to somehow work with the attributes of an example, for instance, lab test results for a single patient, and use that to make a prediction about the label, for instance, whether they have chronic kidney disease or not. And we're going to use training data to help us create such a classifier. Okay, so we're going to start with some historical data. You can think of this as maybe we have a database of historical patients where we know what their attributes were, what their lab tests were, and we know whether it turned out they had chronic kidney disease or not. Okay, so at a high level, this is actually kind of similar to other prediction tasks you've seen, like regression, where regression, we had a data set and then we formed a best fit line, which enabled us to make predictions. Well, now the nearest neighbor classifier, instead of the predictions being a number, the prediction is a class, like chronic kidney disease or not, but otherwise very similar conceptually. And the way the nearest neighbor classifier is going to work, well, you saw it last lecture. What we're going to do when we have a new patient show up at the doctor's office today is we're going to look through our historical data set to try to find the past patient that was most similar to the one in front of me now. And then use the diagnosis for that past patient as my prediction for the patient in front of me now. Okay, so the principle here is the basic idea is that patients with similar lab test results probably have the same diagnosis. No guarantees, but that seems like a good guess. So if I have a new patient where I don't know their diagnosis, but I know their lab test results, I can look through my historical data to find who is the historical patient that's most similar to the one in front of me. And then since those are very similar, I can guess that they'll have the same diagnosis and use whatever the diagnosis was for that historical patient as my prediction for the new patient. Okay, so this is a nearest neighbor classifier. And it works with the training data to help make a prediction. We're going to talk later, maybe Friday, about training data sets and test data sets and where these come from. Now, I want to do a worked example. And I found an awesome example that is so cool. This is from a high school science fair project from a high school student named Brittany Wenger, whose science fair project was so cool it made it to a national competition in 2012. And not only made it to the competition, but won the competition for the best science fair project in the nation that year. And what she did in her science fair project was that she built a classifier that could predict whether a tissue sample indicated breast cancer or not with 99% accuracy. And here you can see a picture of Brittany having meeting President Obama, who's congratulating her on winning this competition. So we're going to try to follow in Brittany's footsteps. Brittany got a classifier that got 99% accuracy using some pretty complicated methods that I can't show you. It's too much for this class. So we're going to use a simpler method. We're going to use nearest neighbor classification. And we'll see how good we get. We're not going to do quite as well as Brittany, but I think it'd be pretty impressive. So let me talk to you about what task Brittany was using classification for. She was using this to look at a tissue sample and distinguish whether it is benign, non-cancerous, or malignant, meaning you have a cancerous tumor. And traditionally, physicians would do this by taking a biopsy. But many physicians were kind of really hoping for, noticed that that there's a way they could take a less invasive a tissue sample that doesn't require cutting into you, but just using a small needle to take a much smaller tissue sample. But it's more challenging to interpret. So Brittany was working with images from this less invasive procedure to see if this less invasive procedure could be good enough to tell for patients who had a lump in their breast whether or not that was likely to be cancerous or nothing to worry about. Okay, so the doctors would take this tissue sample with a needle, and they could do it right in their office. And then the tissue sample would go to the lab, where it'd be placed in a slide and stuck under a microscope. And a lab tech would be looking at images like the left one or the right one. And experts in medicine, domain experts in this went to talk to the trained technicians about how when they looked at a sample under the microscope, what did they use to try to tell that the left one was benign and that the right one was malignant? And they came up with a number of different attributes of the cells that are pictured here that are somewhat indicative of whether it is malignant or not. And so they came up with different attributes like the uniformity of the size of the cells. If they're uniform, that's more likely to be benign. The average diameter of the cells, all sorts of different characteristics of this image. And so what Brittany was looking to do was, instead of having a lab tech look at this by eye and use their experience to try to make their best assessment, Brittany was trying to automate this. So we would have a lab tech who looks at these images and scores them on these different attributes, like the uniformity of cell size and so on, and then use the classification algorithm to make a prediction from those numerical attributes. Okay. Any questions about what we're trying to do here? All right, let's take a look at some data. So Brittany had a data set. And if I can get my computer to wake up, I will show you this data set. All right, so Brittany had a data set collected from historical patients where they both had this less invasive procedure followed, and also the doctors knew whether it was malignant. Maybe they followed that patient over time to see whether it turned into malignant cancer, or maybe they used a gold standard biopsy routine. And each row here represents one historical patient. And you can see the columns are these different attributes that the image is categorized by, like how thick the clump is, and uniformity of cell size, and uniformity of cell shape. Each one of those are rated as a numerical score from 1 to 10. And then the last column you can see here is the class column. That's the label. And that indicates whether for this patient that skin mass was benign or malignant. 0 means benign, 1 means malignant. So 1 is cancer and 0 is not cancer. And if we take a look at this data set, then if we group by class, then what we see is there's a bit over 400 patients in this who had benign, and 200 or so that had malignant. So maybe 2/3 of these are benign. Now, when you get a data set like this, or any data set, as we taught you in this class, often one of the first things that's useful to do is to start visualizing the data set, do some exploratory data analysis to understand the data you've got. And I'm not going to walk you through all of that, but I'm just going to show you an example here of what happens if we take a look at 2 of these attributes, the bland chromatin and single epithelial cell size. I have no idea what those are, but let's just scatter plot all the data points by those two attributes and ignore all the other attributes. And you can see here that there's a color coding. So the blue dots are the benign, and the yellow dots are cancer. Okay. So take a look at this. One thing, there are three colors of the dots. Yeah, what's going on here? This one looks, it's a funny, like, I don't know, an orangish color. And actually, I said there were 600 patients. Does this look like 600 patients? No, doesn't look like 600 patients. So what happened to all the dots? Yeah, there's overlap. We have some patients that have exactly the same value for both of these attributes. And then the dots get plotted on the same place, and they get plotted on top of each other. And so this slight funny color here has some blue dots and some yellow dots. Actually, there's a lot of overlap here because these attributes are only integers, 1 through 10. They're never like 1.73. There's a lot of overlap. And this visualization is kind of problematic. It doesn't really show us how much overlap there is or where the patients are. Maybe there's lots up here and there's lots overlap here, or maybe there's lots down here. You can't really tell from this. So we actually need a better visualization. And there's a number of different ways for building a visualization that can deal with this. But the one that I'm going to use in this notebook, it's pretty easy, is that I added a little bit of noise to each data point just for visualization. I'm not going to actually work with the noisy data for classification, but just for purposes of visualizing, each dot I randomly jittered a little bit, and then I display all 600 dots. And now you can get a picture that looks like this. Okay, so now we can see there's a lot of patients. There were a lot of patients here before. It looked like a single dot, but actually there's many dozens of patients that all are here at 2-2. Okay, so take a look at this picture and help me decide what kind of predictions we would make with a nearest neighbor classifier. For instance, if I had a new patient walk into my office today, I don't know what their diagnosis is, but I can tell that they're at 10-8 at the point where my cursor is. What would you predict is their diagnosis? Class 1. Yeah, malignant. Why? Yeah, the nearest neighbor. If we're using this nearest neighbor technique, we look for the most similar historical patient. In other words, the nearest point in the scatter plot, and the nearest point is a yellow dot that's right near it. What if I had a patient who walked in and was right here? What prediction would I make? I'd make 0, right? Benign. What if I had a patient who walked in and was right here? Or maybe even here. Yeah, the nearest is a blue dot, so also a 0. So there doesn't have to be any data there. I could still make a prediction. Okay, so this is how a nearest neighbor classifier would work. Now, what do you think? Do you think we're going to do a good job of predicting here? Do you think we're going to be able to get like 99% accuracy based on this visualization if we use these two attributes? No, there's overlap. Yeah, you're kind of noticing there's some region here where there's some overlap, where there's some yellow and some blue in this area. So patients who are falling in this area, we kind of don't know. We could make a guess, but our guess might be wrong some fraction of the time, because some of these patients who have test result whose attributes fall around here, some of them it's going to be benign and some of it's going to be malicious. So you can still build a classifier, and your classifier can make the best prediction it can, but this probably going to be wrong. Well, I don't know how often, but I'm guessing more than 1% of the time anyway. Okay, so we could do something. There's a lot of patients we could make a pretty good prediction for, but maybe it's not quite as good as we might hope for because of the overlap that's around here. And it's kind of hard to see, but I think there might even be some overlap here based on the color of some lighter dots down here. So what could I do when I have this situation where I see some overlap and I was really wishing for a better classifier than I think I'm going to get? And I'm going to give you a hint: dolphins. Yeah, yeah, yeah. Use Professor Annie's dolphin picture. We saw what to do last lecture when you had some overlap. A very reasonable thing to try might be to look for more information about the patient that will help you resolve these cases. Like look for a third dimension, a third attribute that might provide additional information that helps you make a better prediction. And that's kind of logical, right? Like the more information I have about a patient, it sort of makes sense that maybe that could help me make a better diagnosis or better prediction. So the more attributes I have about this image taken under the microscope, maybe I have a better chance at making a better diagnosis. Okay, so very reasonable. We could look for a third attribute and then try to do a 3D plot. What if we still saw some overlap when we did that 3D plot? Okay, 4. If 2 wasn't enough, try 3. If 3 wasn't enough, try 4. Anyone want to try to visualize what that plot's going to look like, that 4D plot? Oh my goodness. No thanks. So very reasonable to start using more and more attributes to try to help us make a decision, but then it's very quickly going to get very difficult to visualize. So what are we going to do? How are we going to make a classification decision? Remember, we said nearest neighbor. I'm looking for the most similar point. The most similar point was the nearest one. In other words, the one that was at the smallest distance to it. It's going to be a little hard to do that by doing a visualization. But here's where we get rescued by math. I don't actually need to be able to plot this to be able to compute the distance between 2 points. I can compute the distance between 2 points just knowing where they are. So all I'm going to need is a way to get a formula for the distance between 2 points. That's easy in 2 dimensions. Actually, in 3 dimensions, it's possible. And if I can work out how to do that in 4 dimensions or 5 dimensions or n dimensions, then I'm going to have a way to do classification that will let me use more than just 2 attributes, but 3 or 4 or n attributes. And I won't need to be able to plot it. I just need a way to compute distances. Okay. So one thing we're going to need to be able to do nearest neighbor classification is how to compute distances. All right. So that's what I'm going to show you next, is how to compute distances. I want to stop here and see if you understand where we're going and what the broad picture is, and any questions so far. Yay. Okay. So the next thing I need to talk to you about is how to compute distances. Now, in 2 dimensions, it turns out that computing distances is not too hard. It's like, oh boy, bring in that high school geometry class. It's Pythagorean formula. It's this a squared plus b squared equals c squared business. If I have one data point that's at x1, y1, and I have another data point that's at x0, y0, to compute the distance, I can form this right triangle here. And the length of the side of the bottom of the triangle is easy to compute. That's the difference between the 2 x values. And the length of the vertical side is easy to compute. That's the height, the distance between the 2 y values. So the difference between the 2 y values. And if I want to compute the length of the hypotenuse, then I use a Pythagorean formula for that. I know that the sum of the squares of the side lengths is equal to the square of the hypotenuse. So the length of the hypotenuse is the square root of the sum of squaring these 2 values. And that gets me the formula that's written here. See, the distance between these 2 points is the length of the hypotenuse of this triangle. Okay. Yeah, there is some connection here to RMSE. You're right. You're right. RMSE is a kind of a distance, actually. It's one reason why we use squaring. It helps this analogy to a distance. But okay, that's a side note. So this is how you compute distances, the distance between 2 points if you're in 2 dimensions. Turns out you can do the same thing in 3 dimensions. So if I have 2 dimensions, I get the formula I just showed you. In 3 dimensions, the generalization is very natural. I compute the difference in their x values, the difference in their y values, and the difference in the z values. I square all of those, I add them up, and then I take the square root. And you can see the pattern that's forming here. So if you want the distance in 4 dimensions, you probably know what to do. You compute the differences in all 4 attributes, and you square them, and you sum them, and you take the square root. Okay. So this will work for any number of attributes. In other words, any dimensions. This is how you compute the distance in n dimensions. Even though we can't visualize it, the formula is pretty straightforward. Okay, so now we have a way to compute distances, which means that we have a way to figure out what's the nearest neighbor to a point, which means we have a way, we have all the pieces that are going to be needed to do nearest neighbor classification, and it's going to work even with more than 2 attributes, even if I can't visualize the data set. Okay, so let's do this in code. Let's implement this. Let's implement a Python function to compute the distance between 2 points. And now it might be in 2 dimensions, or it might be in 3 dimensions, or it might be in more. And I'm going to assume the points are represented as arrays. So remember what this formula says. The formula says compute the difference between the first attribute and the differences between the second attributes and the difference between the third attribute, difference between all the attributes. Now, you can see I'm kind of doing the same thing on each attribute. Anytime I'm doing the same thing on each attribute or each element of an array, what should you be thinking about how to implement that in Python? A for loop could work. A for loop could work. Completely legit. There's actually another way you could do it. You could use array arithmetic, array operations, and that will do the same thing on every element in the array. So if I write the difference between these 2 arrays, that's going to compute the differences between each elements, the differences of the first attribute, the differences of the second attribute. And then the formula tells me I should square those differences. Well, this is going to compute the square of each one of those. I'm going to get a new array with all these squared differences. And then the formula tells me to add those up. So I have an array of squared differences. So let's add those up. And then the formula tells me to take the square root after I've added them up. And so it should look like this. This might remind you a lot of how we did the RMSE calculation. It's pretty much the same code. So that will let me compute the distance between 2 points and in a number of dimensions. Now, in my data set, that's represented as a table, and each point or each patient is a row in the table. So I'm going to compute the distance between 2 rows. It turns out that the row of a table is not represented as an array. Do you know why? Why in our tables we don't represent rows as arrays? Different data types. Yeah, different columns might have different data types. So in this data set, all of them are ints. But in other tables, they might not be. They might be mixed. So you couldn't use an array in general. For this kind, though, you can see they're all ints. So what we're going to do is we're going to need to get that as an array. We could represent it as an array for this data set. So I want to compute the distance between 2 rows. So what I'm going to first do is convert each row to an array. And then I'm going to compute the distance between those arrays. And that will give me the distance between two rows. And this distance measures the similarity of the rows. So two rows that are similar will have a small distance, and two rows that are very different will have a large distance between them. All right, so let's do an example. We're going to try computing a distance here between two rows. How about between this first row and this second row? All right, so the distance here between the first row and the second row, between these first and the second patients, is 11.9. Okay. Hard to interpret that number, but let's try and see what the distance is between the first and the third. You can see the distance between the first and the third is much smaller. It's only 2. And maybe that kind of makes sense. If you look here, the first and the third are very similar, right? It's pretty similar numbers here. Pretty similar between the first and the third. Okay, there's a 1 versus a 2. A lot of them are the same. So it makes sense. The first and the third should be very similar, so they should have a small distance between them. But if you look at the first and the second, they're pretty different, right? 2 versus 7, 1 versus 5. They're different like every place, and there's a pretty big difference. So the difference between the first and the second row is they're pretty different, so they have a high distance. There's a large distance between the first and the second. Okay, so this distance is giving you a notion of how similar they are. And last, we can do a little cross check. Suppose I compute the distance between the first row and itself. What do you think that distance should be? 0. Yeah. 0 distance. It's this point to itself. Okay. So we now have a way to compute distances. So let me just summarize what we did here in code and then show you what we're going to do with that. So we use some Python code here to work with rows of tables. And this data set and the data sets we're working with, each row will be all the data for one individual, like one patient. The .row operation will let you extract a particular row from the table. If you want to get the value in a particular column, then you first can get the row and then use .item to get out the number in one column in that row. If all the values are numbers, then you can get the row and then convert it to an array by using np.array function. Finally, one of the things we're going to do with the rows is we're going to do something on all the rows, go through all the rows of the table and do something with them. That's sometimes called enumerating through the rows of the table. And so there's a convenient Python way to do that in Python. If you write a for loop where you say for row in t.rows, what that's going to do, t.rows is like a list of all the rows in the table. So this is going to iterate through the rows one at a time. This for loop is going to, if you have a table with 77 rows, this for loop is going to go through 77 iterations. The first iteration, row will be assigned to the first row of the table. In the second iteration, a row will be assigned to the second row of the table, and so on. And then in each iteration, you can do something with that row. How is this different from num rows? Num rows is the number of rows. So the number like 77. T.rows is like an array or list of all the rows themselves, not just how many there are, but the actual rows. Finally, if you want everything but one row, you can use the exclude operation, and that will give you a new table that has everything but one row. Can I explain the second bullet point? Sure. T.row sub I, if T is a table, the row operation will extract out a single row, the row with index I. So if I did t dot row parentheses 2, that would extract a row, actually the third row, because remember indices start from 0, 0, 1, 2. So t dot row of 2 would give me the third row in the table. And then dot item is an operation that you can do on rows to pull out one of the attributes. And J is the index of the attribute. So if J was 0, that would say, give me the value of the first attribute, like the first column of that row. So dot item is something that you can apply to a single row. And so it's going to give you a single number, not an array. Okay, so let's use this, see how we're going to use this for nearest neighbor classification. In nearest neighbor classification, we're going to want to find the nearest neighbor, and nearest is going to be defined by distance. So we now have the tools needed to do that. And actually, in what's to come, I am going to do what's called k nearest neighbor classification. So instead of finding just the nearest neighbor, I might find the 3 nearest neighbors, or the 7 nearest neighbors, or the k nearest neighbors. So like maybe the 3 most similar historical patients. And then look at the diagnoses for all 3 of those and take a majority vote among those 3. Any idea why I might want to do k nearest neighbors instead of just the single nearest neighbor? Noise. Outliers, prove accuracy. Yeah. So let's look at an example here at this this data set. Maybe if I had a patient who was right here, if I use the nearest neighbor classifier, the nearest neighbor is a blue dot. And so the nearest neighbor classifier would predict benign. But you can actually see that there's multiple neighbors. There's some other yellow ones around there. There's 2 other yellow ones right close by. So maybe, I don't know, maybe in this case, it would be better to predict malignant. Maybe you can see a better example of that, like, I don't know, one of these like right over here. Like if I was right here, maybe that one blue dot would happen to be my nearest neighbor, but there's all sorts of yellow ones around it. Okay, so we might get a more reliable classifier if we look at the 5 nearest points. Because if there's one blue dot that's an outlier that's just kind of way out in the middle of nowhere, we won't get thrown off by that because we're looking at the 5 nearest points. Maybe. So maybe it's better. There's no guarantee that it's better or worse. It's going to depend on the data set what's better, but that's a reason why looking at multiple nearest neighbors might, in some cases, help give you better predictions. Okay. So in the k nearest neighbors classifier, we're going to find the k nearest neighbors to the example, and then use the class of those k nearest neighbors to predict the class of the example. All right, so let me talk you through how to do that. Is there a best k value? There is no universal best. There is no rule that says always use 7. It's going to depend on the data set. For some data sets, maybe the best is a larger value of k. For some, it's a smaller value of k. There's really no way to know in advance what's going to be the best. And so there may be a trial and error process where you try different values of k and see how well they each work and which one works best for the data set you've got. Okay, so we need to know how to find the k nearest neighbors to an example. And we're going to see how to do that in Python. And here's going to be the general procedure. And we're going to compute the distance between the example and everything, each item in the training set. So that's a whole bunch of distances, one distance to each item in the training set. We're going to add those distances as a column to the table of training data. We're going to then, to get the k nearest or the k smallest distances. So if we sort by distance, the ones that are nearest will rise to the top, and we can take the first k rows of that sorted table. And that will give me the k nearest neighbors. Then I can use that to build a classifier. So to classify an example, I'm going to first find its k nearest neighbors. I just talked about how we're going to do that in Python. Then look at the class of those k neighbors and take a majority vote to see which class appears more often. And whichever is the more common one is the one that I'm going to use as my prediction for this example. Okay, so let's write this in code. I've broken this down into multiple steps. So this is really good coding practice. Whenever you're trying to do something complicated, like a nearest neighbor classifier, is identify a bunch of different steps that you're going to take that each is going to get you a little closer to the solution. And then maybe you write one function per step, and the functions can call each other, and that will help you organize your work and keep track of what you're doing, so that you only have to write a few lines of code at a time and can think clearly about what you're doing. So first, I'm going to write a function to do this first step, where we're computing the distance between the example and each thing in the training set. All right. So the procedure that we said was we're going to iterate over the entire training set to compute the distance to each one. So let's do that using this Python syntax that we mentioned before. I am going to iterate through the training set. And for each row in the training set, I'm going to compute a distance. The distance between that row from the training set and the example that I'm trying to classify. And I'm going to put all of this into an array. So that I can add it as another column. The table. So this generates a new table that's the training set, but with an extra column that is the distance to the example for each item in the training set. Okay, so let's take an example here. Let's suppose that my example is this patient here. And then I'm going to take as my training set everyone but that patient. And I'm going to compute, well, let's compute the distances. And here are the distances. So for each patient in the training set, you can see that I've got all the data about them and then the distance to the example. And if I then sort those by distance to the example, change the name of that column. If I sort them, you can see it's brought the ones that have the lowest distance. In other words, that are most similar to the top. And so if I wanted a 5 nearest neighbor classifier, I would take the first 5 rows. And what prediction would I make for this example if I used a 5 nearest neighbor classifier? 1, because you can see here, there's 4 votes for class 1 and 1 vote for class 0. Okay, so I would predict class 1, in other words, malignant. Okay, so we're going to, let's use this to now figure out how to find the k nearest neighbors to an example. And we just saw how to do that. What you do is you compute this distances table, and then we sort by the distance, and then we're going to take the first k of them. Okay. All right. I need a parenthesis in there. And so that's now just going to do this procedure that I just showed you. So for instance, if we run it on this same data set here, then we got those same first 5 rows we were seeing before. So this is the first step in building the K nearest neighbor classifier. This is showing us how to find the K nearest neighbors. Next, we're going to need to write Python code to take the majority vote, and that'll be our prediction. And on Friday, I'm going to finish up working through the code so that you can see the code of how to build a K nearest neighbor classifier. And then we're going to get to the highlight. We're going to see how well does it work on this breast cancer data set, and how well did we do compared to Brittany. I will see you on Friday. Don't forget to go to lab this week. Bye.